we have studied the crystal field theory. The crystal field theory for octahedral complexes, tetrahedral complexes, and even the square planar complexes, how the splitting of the d orbitals takes place. Today we take another important the application of the crystal field theory, how to apply the crystal field theory to the properties of the coordination compounds. The two important properties of coordination compounds are they are color and they have the magnetic properties. Today, let us we take these two properties, how this can be explained based on crystal field theory. Coming to the first one, colors of the coordination compounds. As we know, coordination compounds are colored, and generally these are formed from the transition elements, that is the d block elements, naturally the central metal ion. The transition metal ions having one or more unpaired electrons in their complexes show characteristic color both in solid and in aqueous form. The color of the complexes of any metal ion depends upon the nature of the ligand, oxidation state of the metal, and geometry of the complex. To know about this, the color, you must know the cycle known as the Munchen color cycle. We know that the visible light contains 7 colors, that is violet, indigo, blue, green, yellow, orange, and red. Among the 7, leave the indigo, which is a very small part of it, and the 6 colors. I have written the 6 colors here, that is starts from violet, leave the indigo, you get blue, green, yellow, orange, red in this fashion. And here, if a compound absorbs violet color, it emits yellow color, that is called the complementary colors. Suppose, as you know, the copper sulfate solution or the copper complexes are blue in color, they show blue color, it is because it absorbs the radiation corresponding to in the region of red to orange color. Among these 6 colors, the 3 basic colors are red, blue, and yellow. When you mix red and blue, you get violet color. When you mix blue and yellow, you get green color. Similarly, when you mix red and yellow, you get orange color in between the two. So therefore, to explain any color, the complex absorbs the one color and its complementary color will be exhibited. If the complex absorbs the visible light wavelength corresponding to yellow color, then it emits its complementary color, that is violet. Hence the complex looks violet. Sometimes this may be in the shadows. Sometimes the compound cannot absorb exactly the wavelength corresponding to yellow. If it is in the range, then complementary color also will be in the range. Sometimes it may be in the violet blue color, violet red color, depending upon the exact wavelength that is going to be absorbed. The complex, the cupramonium, the tetra aqua copper 2, the complex looks bluish green. See the bluish green where it comes. Yes, it looks bluish green because it absorbs the visible light wavelength of red color. That is known as the complementary color. Hexamine copper 3 ion shows orange to yellow color because it absorbs complementary color wavelength corresponding to blue color. I have given here the list, that is the color absorbed and the compound transmitted its color. If the compound absorbs infrared radiations, the compound looks white. If it absorbs red color, it looks bluish green. Orange color, it looks blue. Yellow color, indigo to violet. The yellowish green color, you get violet color. Green color, you get purple. Bluish green, that's why I'm saying the shades. The bluish green, it looks red. Blue color, it looks orange. Indigo, if it absorbs, it looks yellow. If it absorbs violet color, it shows yellowish to green. If it absorbs ultraviolet radiation, it looks white because our eye cannot detect infrared radiations and ultraviolet radiations. How do we explain this, the color? In case of transition metal complexes, the energy difference between the two sets of d orbitals, that is the CFSE or delta or 10dq, is usually small. That is T2G to EG orbitals in octahedral complexes and E to T2 orbitals in tetrahedral complexes. This transition of electron from one set of d orbitals to another is called DD transition. This transition can be achieved by the absorption of low energy radiations of the visible region. When the visible light falls on the solution of a coordination compound, electron from the lower energy level get promoted to higher energy level due to the absorption of light of a characteristic wavelength. Rest of the light gets transmitted. The transmitted light has a color complementary to the absorbed color. As a result, the solution of the complex exhibit complementary color. Here I have shown once again the same color V. So the violet, the same what I have said in the form of the color. So if a compound absorbs violet color, then that complex looks yellow color. If it absorbs green color, the complex looks red color, and so on. Here in this table, I have shown the various complex compounds and they exhibit which color. So these are the list of the complex compounds exhibiting the colors. This is one more the same thing. I have given the color of visible light and complementary colors. Here I have given a specific, the wavelength. If the absorbed wavelength is in between 380 to 420 nanometer, then the color absorbed is violet and you get the outcoming color or the complex looks green to yellowish. And if the absorbed wavelength is between 470 to 500, then absorbed color will be bluish, blue-green, and the complex looks red color. The same thing what I have explained in the earlier case, and here I have given even the wavelengths. At what wavelength it looks what color. we know that the octahedral complex of tetra aqua titanium 3 ion contains one electron in a D1 system. In ground state, this electron occupies to T2G orbital. It absorbs radiation in the green and yellow region around 500 angstrom wavelength. The energy corresponding to this wavelength as calculated by the above expression is about 240 kilojoules per mole. This energy is therefore equal to the CFSE of octahedral system, which is required to excite the solitary electron to one of the EG orbitals. Since radiation from green and yellow regions are absorbed by the complex, the solution of the complex looks purple, which is complementary color of the absorbed radiations. Since the difference in energy levels of T2G and EG orbitals vary with the nature of the ions, the nature of the ligands, and the geometry of the complexes formed, they absorb radiations from different regions of the visible light. Thus, the octahedral hydrated cobalt-2 complex, that is COH2O6 times 2 plus, absorbs in the blue region of the visible light. Its aqueous solution therefore appears red color. The tetrahedral cobalt-2 complex of the type COX4 2- ion need smaller energy for the excitation of their d electrons. Since the previous one is octahedral complex and the latter one is tetrahedral complex, since the CFSE of tetrahedral complex is smaller than the octahedral complex, it absorbs in red regions of the visible spectrum. Therefore, the tetrahedral complexes, they appear blue in color. Similarly, it may be mentioned that since hexammine cobalt-3 complexes needs larger energy for excitation of its T2G electrons, it absorbs in blue regions. Hence, it appears orange in color. It may be noted that only those transition metal complexes are colored which have incomplete d subshells and in which the excitation of electrons from lower energy set of d orbitals to a higher energy set is possible. The transition metal ions having completely filled or completely empty d subshell are colorless. Thus, the complexes of Cu plus 1, that is the cuprous complexes having D10 configuration, zinc complexes having a D10 configuration, silver plus ion having D10 configuration, scandium 3 having a D0 configuration, titanium 4 having D0 configuration, etc. are colorless. So these are the some of the points which you have to remember regarding the color for the transition elements. Coming to the another property, that is magnetic property of metal complexes. You have studied in the earlier class, we have three types of magnetism: the paramagnetic, diamagnetic and ferromagnetic. Paramagnetic substances are those which are attracted by the magnetic field. And you know it is due to the presence of unpaired electrons. Diamagnetic substances are those which are repelled by the magnetic field. It is due to the presence of paired electrons or absence of unpaired electrons. Ferromagnetic substances are those which gets magnetized and they behave like a magnet even after removing the magnetic field. Let us our study restricted to paramagnetic and diamagnetic substances in complex compounds. An electron in an atom produces magnetic field because of its orbital and spin motion. This magnetic field strength is measured in units of Bohr magneton, which is given by Bohr magneton is equal to, or magnetic moment is equal to, Eh upon 4 pi mc, where E is the charge on the electron, H is the Planck's constant, m is the mass of electron, c is the velocity of light. The value of magnetic moment, that is Bohr magneton, as obtained by the above expression is 9.274 into 10 raised to minus 21 erg per Gauss. If an orbital contains paired electrons, the magnetic moment of one electron is cancelled by the equal and opposite magnetic moment of the other. Such substances get repelled by an applied magnetic field and are called diamagnetic substances. A substance having orbital with one or more unpaired electrons has a definite magnetic moment and it is attracted by a magnetic field. Such substances are said to be paramagnetic. The greater the number of unpaired electrons in a substance, the greater is the magnetic moment. It has been shown that magnetic moment of a substance containing n number of unpaired electrons is approximately equal to root of n into bracket n plus 2 in Bohr magneton unit. Keeping this, you can calculate. Suppose if a complex contains one unpaired electron, then the n will be 1. So root of 1 into bracket 1 plus 2 will be root 3. Root 3 is nothing but value 1.73. Similarly, if the complex contains two unpaired electrons, then substituting the value n as 2 in the above equation, we get 2 into bracket 2 plus 2. That is, the 2 plus 2 is 4 and outside it is 2, it becomes root 8. So root 8 is nothing but 2.83. Similarly, you can calculate the number of unpaired electrons 3, 4, 5 and their magnetic moment value will be 3.87, 4.90 and 5.92. So through the experiment, if you calculate the magnetic moment, then you can assume how many unpaired electrons are there in the system. Based on the unpaired electron, we can also find whether the complex is low spin complex or high spin complex. The number of unpaired electrons in a given coordination compound of known geometry can be easily predicted. If we know whether the complex is low spin or high spin, magnitude of 10 dq and pairing energy play an important role in this direction. If pairing energy is greater than the CFSE, the crystal field stabilization energy, the electron will not pair up and the complex will be high spin complex. If CFSE, the delta, is greater than pairing energy, the electron will prefer to pair up and the complex will be low spin complex. Thus, the complexes with weak ligand field are high spin complexes or paramagnetic, and those with strong ligand field are low spin complexes or diamagnetic or low magnetic character. Let us take some of the examples here. So we take hexafluoro cobalt 3 ion is paramagnetic, while hexamine cobalt 3 ion is diamagnetic. How we explain this? In both the cases, cobalt is in +3 oxidation state and its electronic configuration becomes D6. Atomic number of cobalt is 26. Atomic number of cobalt is 27 and hence its electronic configuration becomes 3d7 4s2. Its primary oxidation state is +3. Remove the 3 electrons. So therefore it becomes 3d6. When it becomes 3d6, in case of COFC, here pairing energy is greater than the crystal field stabilization energy. And as a result, energy difference between T2G and EG is less. When this is less, the electron prefers to go to the higher energy levels. So therefore, the electronic configuration becomes T2G4 EG2. So as a result, this complex is having high spin complex. It contains the 4 unpaired electrons. The magnetic moment of this complex corresponds to the 4 unpaired electrons. In case of hexamine cobalt 3 complex, here the energy difference between T2G and EG is high. Therefore, the electrons prefers to pair in T2G orbitals. As a result, all the 6 electrons gets paired up. There is no unpaired electron. Therefore, this complex will be diamagnetic in nature. The experimental studies also proves the diamagnetic nature of this complex. Let us take some of the problems how to calculate the magnetic moment. Calculate the magnetic moment of the complex containing 1 unpaired electron. Very simple. Substitute the value 1, that is n is equal to 1. Calculate, it becomes 1.73 Bohr magneton. Coming to the another one, calculate the magnetic moment in tetracyano nickel 2. When I give a name of the complex or a complex, you must able to find out how many unpaired electrons are there. In this, the nickel atomic number is 28. Its electronic configuration becomes 3d8 4s2, and the cyanide is a strong field ligand, and also nickel is in +2 oxidation state. Therefore, the electronic configuration becomes 3d8. And all these 3d8 electrons, so among that, they get cyanide is a strong field ligand, as I said, hence it pairs the electrons. When it pairs the electrons, so we get the number of unpaired electrons in this system will be 2. So when 2 unpaired electrons are there, then the magnetic moment will be 2.83 Bohr magneton. So take the another problem. Such problems will be asked in the examinations. Calculate the magnetic moment in the complex potassium ferrocyanide. Once again, here you must know the central atom in this complex is iron, atomic number 26, electronic configuration 3d64s2. In this complex, iron is in +2 state, hence its electronic configuration becomes 3d6. Once again, the cyanide is a strong field ligand and all the 6 electrons gets paired up. So therefore, this complex is diamagnetic in nature. Similarly, you take the many examples of this type and calculate the magnetic moment. So the same thing here, I have given the magnetic properties, the paramagnetism, how to calculate the magnetic moment. Here I have given like this the examples. Now, the first one, CONH3 6 times 3 plus. So in hexammine cobalt 3 ion, the cobalt is, atomic number is 27, 3d6 4s2, and it is in +3 state. So when it is in +3 state, the electronic configuration becomes 3d6. Ammonia is a strong field ligand. All the 6 electrons gets paired up. So here, this is what I have shown, the pairing of the electrons. So here I have shown the pairing of all the 6 electrons, they gets paired up. So therefore this complex is diamagnetic. If I take another complex, so that is the manganese, MnCN6. So manganese is having the atomic number is 25. So 3d5 4s2, and here it is in +3 state, hence electronic configuration becomes 3d4. And cyanide is a strong field ligand, electrons get paired up and we get 2 unpaired electrons. So these 2 unpaired electrons, so hence the magnetic moment corresponding to the 2 unpaired electrons. So ferrocyanide as well as ferricyanide here, that is which contains the 2 unpaired electrons. In case of ferrocyanide, as I have explained, so it contains the paired electrons. In gets the ferricyanide ion, it is having 3d5 configuration which contains 1 unpaired electron. So therefore magnetic moment corresponds to 1 unpaired electron. Now here also I have taken the various other examples. So go through this and find out how to calculate the number of, based on the number of unpaired electrons, the magnetic moment using the equation. So in the case of chromium hexaaqua +2 complex, so it contains the 3 unpaired electrons. So the magnetic moment corresponds to 3 unpaired electrons, that is 3.87. In case of the FeCl6 4 minus. So in this case, FeCl6 4 minus, Fe is in +2 state having D6 configuration, but the chlorine is a weak field ligand. When it is a weak field ligand, it is unable to pair up the electrons, so which contains the 4 unpaired electrons. So the magnetic moment in this complex corresponds to the 4 unpaired electrons, which is around 4.9 Bohr magneton. Coming to the next one, how to determine the magnetic moment of the complex. So 2 commonly used methods of determination of magnetic moments are the Gauss method, another one is Faraday method. Let us we restrict our study to the Gauy method of determination of magnetic moment. In this method, the Gauy balance is used to measure paramagnetization of the complex by weighing the sample in presence and absence of magnetic field. So the substance whose magnetic paramagnetism is to be calculated is taken in the form of a fine powder in a tube. That's what it says. Finely powdered substance or solution is taken in a Pyrex glass tube called the Gauy tube. The substance is weighed first without magnetic field. So take the weight of the compound in absence of magnetic field and then apply the magnetic field and of definite field strength, and then you find out the magnetic field. You find out the weight of the substance. Depending upon the magnetization, the weight of the substance increases. If the compound is more magnetized, then the weight of the substance will be more. If the compound is less magnetized, then the weight of the substance will be less. This more magnetization and less magnetization depends upon the number of unpaired electrons. However, if the complex is diamagnetic, the weight of the complex decreases. Larger the number of unpaired electrons in a substance, greater is the increase in its weight in a magnetic field. Now, how to do the calculations here? The magnetic moment cannot be measured directly. We first measure the magnetic susceptibility known as chi, given by that symbol, from which it is possible to measure magnetic moment. The magnetic susceptibility is a measure of the capacity of a substance to take up magnetization in an applied magnetic field. It is given as chi is equal to m upon h, where m is the mass of magnetizing material and h is the applied magnetic field strength. Molecular magnetic susceptibility is calculated using the equation chi m is equal to 2L into delta m divided by h square into m into capital M, where L is the length of the string, that is how the material to be weighed, that's the length of the string, and delta M is weight change in presence and absence of magnetic field. H is the applied magnetic field strength, M is the actual weight of the substance, and capital M is the molecular weight of the substance. Knowing the magnetic susceptibility, that is chi m, magnetic moment can be calculated using the equation mu square is equal to 3 kT up into chi m divided by n naught, where the k is the Boltzmann constant, T is the absolute temperature, and n naught is. This is what I am showing. In this, the substance is placed between the two magnetic field, and if the substance is paramagnetic in nature, then the weight of the substance increases. If it is diamagnetic in nature, the weight of the substance decreases. So below I have shown a Gauy balance, so where the substance is placed between the two magnetic fields. So based on knowing the difference in weight, so the magnetic moment is calculated. Before to calculate the magnetic moment, magnetic susceptibility is calculated. Students, go through these aspects and try to learn about these things.